Introduction to sound travel. Sound travels as a mechanical wave through various mediums, including gases, liquids, and solids. It is generated by vibrations that create pressure waves moving through these substances. Understanding how sound travels and why its characteristics change with distance involves exploring the properties of sound waves and the medium through which they propagate. How sound waves propagate. Sound waves are longitudinal waves that consist of compressions and rarefactions. When an object vibrates, it creates compressions, areas where particles are close together, and rarefactions, areas where particles are spread apart, in the surrounding medium. These pressure changes travel through the medium as the particles bump into each other, transferring energy from one particle to the next and propagating the sound wave. Mediums and speed of sound. The speed at which sound travels depends on the medium through which it is passing. In general, sound travels fastest through solids because the particles are closely packed and can transmit vibrations more quickly. In liquids, sound travels more slowly, and in gases, sound travels the slowest due to the greater distance between particles. For example, sound travels at approximately 343 meters per second in air, 1,480 meters per second in water, and 5,000 meters per second in steel. Influence of temperature on sound. Temperature also affects the speed of sound. In gases, warmer temperatures increase the speed of sound because the molecules move faster, causing more frequent collisions and quicker transmission of sound waves. Conversely, in cooler temperatures, sound travels more slowly due to reduced molecular activity. This effect is less pronounced in solids and liquids but still present. Attenuation of sound with distance. As sound travels away from its source, it undergoes attenuation, or a decrease in intensity. This occurs due to several factors. Spread of energy. As sound waves travel outward, their energy spreads over a larger area, reducing their intensity. This spreading is known as spherical spreading or geometric spreading. Absorption. Sound waves lose energy as they interact with the medium, with some of the sound energy being absorbed by the material or converted into heat. For example, soft materials like carpets and curtains absorb sound, reducing its intensity. Scattering. Sound can be scattered by obstacles and irregularities in the environment, which can also diminish its intensity as it travels. Frequency and distance. The frequency of a sound wave, which determines its pitch, also affects how it changes with distance. Higher frequency sounds, such as those produced by a whistle, tend to be absorbed more quickly and attenuate faster than lower frequency sounds, like those from a drum. This is why distant high-pitched sounds are often harder to hear compared to lower-pitched sounds. Effects of environmental conditions. Environmental conditions, such as wind and humidity, can influence how sound travels. Wind can carry sound waves in the direction it is blowing, causing the sound to travel farther in that direction and attenuate less. Humidity can also affect sound propagation, as moist air is less dense than dry air, allowing sound to travel more efficiently. Practical implications. Understanding how sound travels and changes with distance has practical applications in various fields. For instance, engineers design acoustic treatments in concert halls to optimize sound quality, while meteorologists use knowledge of sound propagation to study atmospheric phenomena. Additionally, the principles of sound travel are important in fields such as sonar and audio engineering. Conclusion. Sound travels as a mechanical wave through different mediums, with its speed and intensity affected by factors such as the medium's properties, temperature, and distance from the source. As sound waves travel, they experience attenuation due to spreading, absorption, and scattering. Frequency and environmental conditions further influence how sound is perceived over distances. Understanding these principles helps in various applications, from engineering to environmental science, and enhances our comprehension of how sound behaves in different settings.